recording. And let me share my screen. Here we go. Okay, let's get rid of that. Close that up. We don't need it. Let's see. Close that up because I don't need it. So let's see. Here we go. So we are in week 9. Guys, I'll have the stuff for week 10 set up by Friday, okay? But let's see. So guys, just a friendly reminder, 4.1, 4.2, and 4.3, those homeworks are due by this evening, okay? So in case you haven't done them, they're due by tonight. 4.2 and 4.3 were pretty short sections. I want to say those were pretty easy to do. 4.1 was related rates. Takes a little bit more time to do. You got to use the chain rule and stuff, but again, that stuff's due by tonight. So let's see. Today, y'all, what we're going to do is, so on Monday we did 4.2 and 4.4. So I guess 4.2 is not due today. It should just be 4.1 and 4.3. Sorry. So 4.1 and 4.3 are due by tonight. So today, y'all, what we're going to do, I don't know why this is 2.5. Let me fix that. It's 4.5 here, and here it says 2.5. Boom. Save it. There we go. Okay, so 4.5, y'all, we're going to do that today, and the homework of that is due a week from tonight, okay? So what I have here is the notes for 4.5. Here we go. Okay, so 4.5, y'all, talks about derivatives and the shape of the graph. Let me make sure that I am sharing the screen. Yeah, we are. And we're recording. Who do we got here with us? Matias. Okay, Matias, I'm glad you're here. Okay, so 4.5, y'all, talks about derivatives and the shape of a graph. So it says, learning objectives. Explain how the sign of the first derivative affects the shape of the function's graph. State the first derivative test for critical points. Use concavity and inflection points to explain how the sign of the second derivative affects the shape of the function's graph. Explain the concavity test for a function over an open interval. Explain the relationship between a function and its first and second derivatives, and state the second derivative test for local extrema. Okay, so first thing we're going to talk about, y'all, something called the first derivative test. First derivative test says that if the first derivative of my function, y'all, is positive, then our function is increasing. Remember what it means for the function to be increasing. All it means, y'all, for a function to be increasing is as I move along the x-axis, say from this point here. So I would call this point here f of a, and I would call this point here f of b. As long as b is bigger than a, all that means is b is to the right of a. Okay, then f of b is going to be bigger than f of a. All it means is that the y values are going to be going up, right? That's what it means for it to be increasing, okay? So anytime my first derivatives are positive, y'all, so let me write that here. When the first derivative is positive, this, when f prime is positive, right, then the function is increasing. When the first derivative is negative, then the function is decreasing, okay? That's what the first derivative test basically tells me. First derivative is positive, functions go increasing. First derivative is negative, the function is decreasing, okay? So it says both functions are increasing over the interval. The derivative is positive. Okay, so let's see. Here we go. So here again, y'all, is an example of where my first derivatives are positive and negative and all that kind of good stuff. Okay, so I want you to sort of look at the picture that I have here. So I'm going to kind of trace it a little bit. The function here is increasing because it's going up. Since the function is going up, the derivative is positive. If you notice from here to here, the function is going down. Therefore, the first derivative is negative. Okay? The function begins to increase again, and it kind of levels out right here, but then it increases again. So the derivative again happens to be positive. And then the function starts to fall down, And so again, my first, or this here is a little typo, y'all. This should say negative. That should be a less than 0 because it's decreasing. Okay, sorry about that. Whoever wrote the textbook, because it's supposed to be negative, okay? So we have critical points. Critical points happen to be at these values right here, where either the derivative is 0 or the derivative is undefined. So y'all, anytime we have like a sharp point like this, when the function does this and it kind of comes back down, the derivative of that value is undefined. But you can see right here, the derivative is equal to 0, the derivative is equal to 0, excuse me, the derivative is equal to 0. Okay. So we're going to figure out a couple of things here. Here we go. First derivative test. And I'm going to explain this to y'all as we go through the problems. But the first derivative test says, suppose f is a continuous function over an interval I containing a critical point C. If f is differentiable over I except possibly at a point C, then f of C satisfies one of the descriptions. If the sign of the derivative changes from positive when x is smaller than c to negative when x is bigger than c, then we have a local maximum. If the derivative sign changes from negative when x is smaller than c to positive when x is bigger than c, then we have a local minimum. And if the derivative has the same sign on either side of that value c, then f of c is not going to be a local max or a local min. Okay. And so look, we'll go through a couple of problems here. Here we go. Here's the first problem. So if we look at this thing here, and again, y'all, this problem here is just a visual problem. We're not going to actually do any calculus at all with this problem here. But it says, consider the function in the graph to the right. The function has a relative maximum of what? Okay, so I'm looking at my picture here. I'm trying to find the maximum, which means what is the highest point in the graph? In terms of, I know the graph is infinite because it goes forever at the endpoints, right? So the graph kind of continues to go like this, and it continues to go like that. But we do have a high point here. What is the y value of that high point? 3. So we say we have a relative maximum of 3 when x is equal to, what is the x value? 0, right? So that point right here, y'all, is a 0.03. So the y value is 3 when the x value is 0. Then we also have a minimum over here. What are the coordinates of this point? 7 and -4, right? So we have a minimum of -4 at x is equal to 7. Okay. Now, we're going to talk about where is the function increasing and where is the function decreasing. Y'all, when I have a problem like this, my approach is, let me draw some vertical lines. I'm going to draw a vertical line right through the max, and I'm going to draw a vertical line right through the min. Okay? Now, remember what it means for the function to be increasing. For the function to be increasing means as I move from the left to the right, the function is going up. So take a look. The function is going up, right? Now, when we're talking about the intervals, y'all, we're referring to the domain. In case you weren't sure, the domain refers to the x value. My question to you guys is, if I'm approaching the x values from the left to the right, okay, up to this point right here, where are we starting on the x-axis? All the way over here on the left. Negative infinity, right? So we're going to go, it's increasing from negative infinity all the way until we hit this x value of 0, okay? Y'all, the function begins to increase again as I move to the right, because the function is going up. So it's going to increase from 7 all the way to where? Positive infinity, right? So we're going to say it's going to increase from 7 to infinity. Because we have two separate intervals, y'all, we use the union. The union just says it's going to be on both of those intervals. It's just connecting the two intervals. Okay? Now we want to know, when is the function decreasing? Well, hey, look, it's decreasing between what two x values? 0 and 7. And that's where our function is decreasing. Okay? Now, with these, we're looking at open intervals. So at open intervals. So I'm not including those endpoints because at those actual points, it's not either increasing or decreasing. At the number 7, it doesn't increase or decrease. That's why we use open intervals. Because who's to say that, well, at 0, it was increasing? Because we're talking about, look what it says right there, interval. So that tells me I'm looking, the 0, 7 is not a point, it's an interval. Does that make sense? This is the interval, yeah, because that's what we're discussing, right? It's talking about an interval. So you have to look at the context, right? Good, good, good. Okay, so y'all, we have a strategy on how we're going to use the first derivative test. Okay, so it says find all critical points of f and divide the interval I into smaller intervals using critical points as endpoints. Analyze the sign of f prime in each of the subintervals. If f prime is continuous over a given subinterval, which is typically the case, then the sign of f prime in that subinterval does not change and therefore can be determined by choosing an arbitrary test point. And then use the sign analysis to determine whether the function f is increasing or decreasing over that interval. Okay, so let me show you what we're going to do here, y'all. First thing we're going to do, because this is called the first derivative test, we're going to take, you guessed it, the first derivative. Okay. Okay, so we're going to do this in pieces. Let's go real slow, see if we can't figure this out. What's the derivative of negative 2x to the third? Negative 6x squared. The derivative of 33x squared is a, okay, and the derivative of a negative 168x is a negative 168. Okay. And then the derivative of 9 is 0, so we're not going to split that part. Okay, we'll get there. Okay, now, y'all, the way we find the critical values is we take the derivative and we set it equal to 0. So look, we're going to have negative 6x squared plus 66x minus 168. We're going to set it equal to 0. Okay. So what I want to do now, y'all, is I want to solve this equation. So since I'm solving an equation, I'm going to go ahead and divide everything by negative 6. Yeah, just to make it a little bit easier. So x squared, everybody agree on minus 11x? And then 168 divided by 6 should be something like 28 equals 0. Okay. Anybody know what the two factors are here, y'all? I'll give you a hint. Those are both going to be x. What am I looking for here? Positive or negative? Negative on both, right? Because I need to multiply to what kind of number? And they need to add up to a negative 11. Okay, so now we set each part equal to 0. We're going to get x equals 7. We're going to get x equals 4. Okay, now that we found these are our critical values, y'all, okay? So those are my critical values. The next thing we're going to do is this. We're going to draw a number line. And we're going to put those two critical values on the number line. Which number should come first? 4. Here is 4. Here is 7. Okay, I want you to think about my number line for a minute. On the left side, y'all agree that way over here on the left I'd have negative infinity, and way over there on the right I'd have positive infinity? Okay, what we're going to do now, we're going to pick test numbers. Numbers that happen to fall in those intervals. So I need a number between negative infinity and 4. Can anybody give me a number? Any number. Now, guys, any number smaller than 4 is going to work. John says 3. I'm actually going to use 0 because 0 is a real easy number to plug in. But you can use 3. I need a number between 4 and 7. 5. And I need something bigger than 7. 10. Perfect. Okay, those are our test numbers. What we're going to do now, y'all, is we are going to use those test numbers to find the sine of the derivative. Okay? So what I'm going to do is I'm going to come back to this function right here, the derivative function. Okay? So I'm going to use my calculator. Let me move this over to the side. Let me turn it on. Oh, there we go. Let me clear this out. So I'm going to enter in yn. I have a negative 6x squared, a plus 66x, and a minus 168. Okay, so there's my function. Okay. What we're going to do now, we're going to evaluate the function, y'all. We're going to evaluate it at each of those test numbers, 0, 5, and 10. Okay, so look, let's do the first one. Let's plug in 0. When I plug in 0, look at the sign of my number. I'm not necessarily interested in the value. I'm only interested in the sign. So the sign of my number is negative. Okay, I'm going to do the same thing again, but now I'm going to plug in the number 5. So I plug in the number 5. I'm going to hit enter. I'm only interested, y'all, in the sign of my number. Sign of my number is positive. Okay. We're going to do this a third time, and we're going to plug in the number 10. Again, I'm only interested in the sign of my number. It happens to be negative. Okay. So now that I have this, we can look at the function f. If the derivative is negative, that means that the function was decreasing. If the derivative is positive, that means that the function is increasing. And then if the derivative is negative, then the function happens to be decreasing again. Okay? Now, before I go on, I want you to think about what we just did. The first step was, hey, let's find the derivative function. Let's set it equal to 0 so we can find our critical value. Okay? Then we draw a big old number line right here. And we put those two critical values on our number line. Okay? In this case, it was 4 and 7. Okay? Then we pick test numbers in those intervals. So anything smaller than 4, any number between 4 and 7, any number bigger than 7. The values of the numbers that you pick, y'all, aren't important because I'm not necessarily interested in the actual value. I'm only interested in the sign of the number. Is the sign of the number positive or is the sign of the number negative? What number do I get? I don't really care. I'm just really interested in the sign. Okay? What I mean by the sign, we're taking those test numbers, y'all, and we're plugging them back into the derivative itself. When we find out if the derivative is positive or negative, that tells me whether or not the function is either increasing or decreasing. Okay? So now, let's take a look at what's going on here. From negative infinity to negative 4, the function is doing what? Decreasing. And then the function goes back up. So since the function is going down, it goes back up. This here, y'all, is going to be a minimum, right? Then the function is increasing, and then it goes back down. So right here, we're going to have a maximum. Okay? So I want you to think about, now when I look at the directions, it says this function has a local minimum. Where did we say we had a minimum at? At what critical value? At 4. Okay? At 4. Now, with the value of what? Well, I don't know yet. what I have to do is I have to come back to the original function, y'all, and plug in what number? Well, at least right now, 4, right? Because that's the one I'm interested in. Okay, so look, y'all, let's do this. Y equals, let's do over here in the second one, let's enter the original function in. Negative 2 x to the third plus 33x squared. Oops, 33x squared. X squared minus 168x plus 9. Okay, there we go. Okay, so let me quit that. Let me go to my y bars. Let's go to our second function now, because the first one was actual derivative. And we're going to evaluate this at 4, and this is going to be my minimum. So look at the minimum value we're coming up with, negative 263. Okay. And then we're going to have a local max at x equals 7, and now we want to find that local max. So again, I'm going to do the same thing we did before, but now I'm going to evaluate this at 7. And look at the max, negative 236. Okay, question. Do y'all agree that this value here is bigger than that value there? Yeah, it is, right? So they're both negative, but it's less negative, right, than 263. And so we found our values. Okay. So we'll do a few of these problems today. Y'all, we're just doing one section today. We're just doing 4.5. We're going to go through real slow. I want to make sure you guys are kind of understanding the process, okay? So we're going to go through a few of them to make sure that we're good, okay? So look, let's try the same thing over here. It says the function f of x is 2x to the third minus 36x squared plus 162x plus 3 has one local min and one local max. Okay, so we want to find them. Okay, number one, y'all, we're going to do it like this just so that we know what we got to do. Let's find f prime at x, okay? So f prime at x is equal to, anybody know what's the derivative here? Yeah, let me get my water real quick. All right, 6x squared. What comes next? Minus, and then plus. Okay, so there's our derivative, okay? Step number 2, find the critical values by setting f prime of x equal to 0. So we're going to take that function that we got, the derivative one, and we're going to set it equal to 0, and we're going to solve for x. Question, do you guys think we can divide everything here by 6? Yeah, let's divide everything by 6. All it does, y'all, is it just makes us doing the algebra part hopefully a little bit easier. So this is going to become an x squared. Anybody know how many times 6 goes into 72? Well, what about into 162? $27. There you go. Perfect. Okay. We're going to solve this part here. We're still doing step number 2. Question. Anybody know how to factor x squared minus 12x plus 27? I'll give you a hint. 2 negatives. Very good. Excellent, Steve. Good. 2 negatives is right. What two numbers multiply to 27 and add up to 9? Or 12, I'm sorry, 3 and 9, right? Minus 3, minus 9. So guys, remember what it is we're doing here. This is just a little algebra trick, but I want to make sure you guys are really good with it. Like I said, I feel like the students in my remedial math, they could do this part just because that's what we do in that class, you know. But anytime the number here is a 1, you're looking for what two numbers multiply to this one and add to that one. As long as the number in front of the x squared is 1. If it isn't, there's a couple extra steps we got to do. If you switch the placement of 3 well, what do we do from here? What's the next step when I'm solving? Set each part equal to 0, right? So if you set each part equal to 0, don't you still get the same numbers? Don't you still get positive 3 and positive 9? Right? So which one do you put first, second? It doesn't matter. Okay, guys, step number 3, draw the number line and put those critical values. So, y'all, I'm not picky about the number line at all. Just put the numbers in order, right? Put the 3 first because that's the one that comes first, right? So I'm pretty lenient with number lines, but don't put 9 and then 3 because it just doesn't work that way. All right, negative infinity, infinity. Okay, we're going to pick our test value. So I need a number smaller than 3. What's the number smaller than 3? 0. Guys, 0 is always a great number to plug in because it's easy to plug in, okay? Now I need a number between 3 and 9. Any number between 3 and 9. 5, okay? And I need a number bigger than 9. 10. Could you pick 20 if you wanted to? Anything is bigger, right? It just happens to fall in those intervals. All right. Now that we do that, y'all, we're going to look at the sign of the derivative. Okay? The sign of the derivative. So we're going to take this value 0 and we're going to plug it into the derivative function, which was this one right here. So look, let me grab my calculator. Let me turn this guy on. Let me go to my y equals. I'm going to clear both of those functions, but I am going to enter in my derivative one first. So 6x squared minus 72x plus 162. Okay. There we go. So let me quit that now. Okay, I'm going to go to my y bars. And we're going to evaluate our function at each of those test numbers, y'all. So the first one we're going to do is going to be at 0. So positive. The derivative is positive, right? All I'm interested in is the sign. Okay, so again, if you notice, all I did is say, what's y of 0? Let's do the same thing, but let's evaluate it at 5. When evaluated at 5, all I'm interested in is the sign. Oh, it's negative. And then we're going to do the same thing again, and we're going to evaluate it at what value? 10, right? And it should be positive. Yes, it is. Okay. Now that we have that part, the third part is the graph of f. If it's positive, that means that the function is increasing. If the derivative is negative, that means that the function is decreasing. And then if it's positive, that means that the function is increasing. So take a look, y'all. This is what my graph is kind of looking like. It does something like this, comes back down, goes back up. This here would be a minimum or a maximum. That'd be a maximum, right? Because it's on top of a hill, right? So what is the x value when we have our max? At 3, right? Not the test number, y'all, but these numbers here. Okay, so we're going to have a maximum at 3, and we're going to have a minimum at what value? At 9, right? Because it's kind of like the bottom of the hill. Okay, so y'all, now what I need to do, I need to find the function of those values. So I'm going to come back to my y equals, and now I'm going to enter in the original function that we had up here, because I need to find the values at 3, and I need to find the values at 9. So I have 2x to the third. Okay. So, y'all, I'm really happy that when I'm teaching this class, that I'm teaching it today instead of in 1993 when I had this class, because doing this right here, having that feature on the calculator, makes this so much easier to do than actually having to plug in the number. You know what I mean? And let's crunch it and all that kind of stuff. This definitely makes it much easier to do. I actually want white too, though. So let me clear that. Let's go bar. One. We're doing the second function here. Okay, so we're evaluating to find the minimum. We're doing this at the value of 9. And at 9, I came up with 3. And then to do the maximum, I'm evaluating this function at 3, and this is going to be my max, and I'm coming up with 219. So far, so good? We're doing okay? Guys, is that doing that, like plugging in the function in the calculator and then just doing the y bars? Is that pretty straightforward on how to find the values? Yeah. So just this little algebra trick. I'm going to show you something real quick, y'all. It's an easy way to evaluate the function without having to do a whole lot of math. Okay. So I don't know if you guys, you might remember this from college algebra. If you don't sweat it. I'm going to show you right now. So what was our function? Our function was y equals, or f of x equals, what, 2x to the third minus 36x squared plus 162x plus 3, right? Okay, so this is just something, y'all. It's a way, if you're going to do it, I mean, I'm not advocating that you do it by hand. I would much rather use the calculator. Guys, the only thing you have to worry about when you're doing this on the calculator is this, that I enter it in the right way. You know what I mean? That's the only, right? That's the only mistake that I can possibly make is that, oh man, look, I put something wrong and I should have put something right. You know, something like that, right? But I don't know if you remember something called synthetic division. Synthetic division, you draw like a little half box, okay? What you do, you're only using the coefficient. So 2, negative 36, 162, and 3, okay? Think of the two values that we evaluated this at. We were plugging in what two numbers? 3 and what? And 9, right? So look, when we plugged in 9, look at the y value we came up with. We came up with 3. Okay, so the way you can do this by hand, if you want to, put the 9 right here. Okay, this is synthetic division. Guys, the first step in synthetic division says drop the 2. Okay, then you multiply. What's 9 times 2? 18. Add straight down. Negative 36 and 18 is negative 8. Multiply again. Okay, I'm going to use my calculator for this because it's 9. It's 9 times negative 18, negative 162. Add those two numbers together. What's 162 minus 162? 0. Multiply again. What's 9 times 0? 0. Add straight down. This number here is going to be your answer. Take a look. When we did this on the calculator, when we plugged in 9, what y value did we get? 3. You want to do it by hand? That's an easy way to do it by hand. It's much easier than taking 9 to the third times 2 minus 36 times 9 squared plus 162 times 9. You know what I mean? If you're going to do it by hand, this is another way you could do it, if you wanted to do it by hand, right? If you don't want to do it by hand, and again, I'm not going to do it by hand. I'm going to use my calculator. But if you want to do it by hand, that's the way you can do it. Guys, you could do the same process and plug in the number 3 right there. And the answer you'll come up with here at the end would have been 219, right? So if I would have done this process again, 2, negative 36, 162, and 3, if I were to put 3 here and continue to going, at the end, the number we would have come up with was, what, 219? That would have been the number right there, okay? Just another way you can go about doing it if you don't want to do using the calculator. But, you know, I'm going to use the calculator. We're in modern times. All right. Let's see if we can do this problem together, y'all. And I'm going to ask you guys a couple of steps. Anybody remember what step 1 is? Find the derivative. Good. Find f prime. Okay. F prime of x. Everyone agree negative 6x squared? Okay. Plus. Minus 180. Okay, good. Step 2, we find the critical values. Y'all remember how do we find the critical value? We do what? What do we do with that derivative? Set it equal to 0. Good. So we divide everything by -6. So x squared minus 11x plus 30 equals 0. Okay. All right. Guys, I'm going to ask you a question. In words, do you remember what it is I'm looking for? Two numbers that multiply to what? 30. Good. And add up to what number? -11. You got it. Okay, what are the two numbers that multiply to 30 and add up to -11? -5 and -6. Good. So everybody agree the two values we come up with are x equals 5 and x equals 6? Excellent. Okay. Okay, so take a look here, y'all. It says, and we're gonna answer the questions as we go through. It says, for this function, there are 3 important intervals: from -infinity to a, from a to b, and from b to infinity. So when I set up my number line, it looks like this, right? Here's -infinity, here's infinity. The two numbers that I'm going to put on my number line are what two numbers? 5 and 6, okay? So look what it says. Find the value of a. Well, the value of a would have been 5, and the value of b would have been 6, because that's the order in which they appear. Okay, now we're going to do our test numbers. I need a number smaller than 5. 0. We need a number between 5 and 6. 5.5. And we need something bigger than 6. 10, 7, 11, 21, whatever you want to use, right? Again, these are test numbers, you guys. The one thing I really want to emphasize, the test number is not important as long as it happens to fall in that interval, right? So it has to be something bigger than 6. Or it has to be a number between 5 and 6. Or it has to be a number smaller than 5. Okay? Now, the next part. Okay, we're going to do this here. Remember what it is we're looking at. We're looking at the sine of the derivative, okay? The sine of the derivative itself. So remember, my derivative here, y'all, I'm going to kind of move this over. I'm going to go to my y equals, put it on. Go to my y equals. Let me clear what I have here. And I'm going to go to my derivative, which is a -6x squared plus 66x minus 180. Okay, that's my derivative. And I'm going to evaluate the derivative at each of those values, right? So the first value we said was 0, okay? And at 0, the sign of the derivative is what? Negative. Good. We're going to do the same thing as we go along, y'all. We're now going to evaluate the derivative at 5.5. The derivative here, positive. And we're going to do this one more time. And we're going to evaluate this at a number bigger than 6. I said 7, John said 10. We could even pick 105. And the sign there is negative. Right? Okay. Now, we're going to look at the graph of x. Since the derivative is negative, do you agree that means that the function is what? Decreasing, right? When it's positive, the function is increasing. When it's negative, the function is decreasing. So again, think about what that looks like, y'all. The function is going down, comes back up, and it goes back up, right? Something like that, right? Something like that. Okay, so look, now it's asking us for each of the open intervals, determine whether f of x is increasing or decreasing. So question, between -infinity and 5, was the function increasing or decreasing? Decreasing, right? So right here, y'all, when you select, you're going to select we're going to select decreasing, right? Okay. What about between the intervals from 5 and 6? If the derivative is positive, that means it is what? Increasing. And then again, from 6 to infinity, wouldn't we say it's also what? Decreasing. Okay. Now, look what it says. At x equals a, and what they're referring to here, y'all, is that x equals 5. Would the function have a minimum or a maximum right here? That'd be a minimum, right? Can I write that? Okay. And then at x equals 6, we have a what? Does that make sense? Yeah? Guys, yesterday morning, I don't have class on Tuesday and Thursday until 3. So usually what I do the day before I meet with you guys, I go over these problems myself. Just to, I want to make sure that when I come in here, not only can I do the problems, but I can explain how I'm going about it, right? So I was doing these things yesterday, and I told you guys about that one business calculus professor I had, and I swear it was the spring of 1993 back in my head, because I remember going over these problems with him. And the funny thing is, that was the very first sort of experience I had with calculus. And out of all the math classes that I've taken, that one is the one that's like more, like it's tattooed in my mind, you know what I mean? Because he was such a good instructor. So what I'm trying to do is like I'm thinking about them like, man, I could, like like March 1993, like I feel like I'm almost right there. And it's funny that I still remember like that experience more than all the other calculus classes that I took. You know what I mean? So that's why, and this is exactly how he taught me. So that's what I'm trying to do with you guys. I'm trying to give you that same experience and break it down like this, right? Because I thought he did such a good job of breaking it down. And okay, what am I trying to do? And what does this tell me? That's the side of the derivative. What does that mean? Well, if the derivative is positive, that means the function's going up, function's going down, that kind of stuff. And we would make these same little like diagram in class, and it helped out a whole lot. So that's why I'm trying to do the same thing here with you guys. Okay, so now we have something that we call concavity, yo. Concavity says let f of x, or let f be a function that is differentiable over an open interval I. If the derivative is increasing over I, then we say f is concave up over I. If f prime is decreasing over I, we say f is concave down over that interval. Okay, so this is what concave up looks like. Concave up, so concave up looks kind of like this. A lot of times, they do kind of like this. This is concave up, and this is concave down, right? So it's just kind of the shape of it. So some people say concave up looks like a cup, concave down looks like a frown, okay? So let's see. We're going to talk a little bit about concavity in a second. It says since f is increasing over the interval a and b, we say it's concave up, and since the derivative is decreasing, then we can say the function is concave down. All right. The way we test for concavity is we look at the second derivative, okay? If the second derivative is positive over that interval, y'all, then the graph is going to be concave up over that interval. If the second derivative is negative, then f is what we call concave down, okay? When the concavity changes, those are what we call inflection points, okay? So when the concavity of the function changes, we call those things inflection points. Let's see. Let me take a look. Let's see. Here we go. So we're going to start looking at the concavity of the function. So the concavity all deals with the second derivative. So step number one, we need to find the first derivative. So let's find the first derivative of this function. If I take a look at the function that I have here, 1/12 x to the fourth, everybody agreed the derivative is going to look something like this, 4 over 12 x to the third plus 3 over 6 x squared. Remember what we said, doesn't this number come down to the front? But I already had a 1/12 in front of it. And then we reduced our power by a power of 1, so it becomes x to the third. This number comes down to the front. There it is. In front of the 1/6 is 3 over 6. And then I reduce my power again. So guys, can I reduce that fraction anyway? Can we reduce these fractions? 4 over 12 reduces to what? 1/3, yeah, x to the third. And 3/6 reduces to 1/2 x squared, right? Okay, step number 2, we got to now find the second derivative of the function. So the second derivative, let's take a look what the second derivative is. What would be the derivative of 1/3 x to the third? 1x squared, right? Good. And what about the derivative of 1/2 x squared? Yeah, 1x, right? Okay. So are we good with that, y'all? Because that 3 is going to come down the front, and this 3 that I have right here is going to cancel with that 3. Does that make sense? Jennifer, we doing okay? All right, just checking with you guys. Okay, what we're going to do now, y'all, we're going to take this derivative, the second derivative, we're going to set it equal to 0. Okay. So step number 2, or step number 3, actually, because step number 2 is find the second derivative. Step number 3, find the critical value by setting the second derivative equal to 0. So I'm going to have x squared plus x equals 0. Okay. So can we factor out an x out of here, y'all? Out of both those parts. So now I have x times x plus 1 equals 0. So when we set each portion equal to 0, well, that's already equal to 0. When I move that 1 over, everyone agree that is a -1? Okay. All right, step number 4. We're going to draw a number line. -infinity and infinity. And the two numbers that I'm looking at here, y'all, are -1 and 0. Okay. We're going to pick our test values again. Okay. I need a value smaller than -1, -2. I need a value between -1 and 0, -0.5. And I need a number bigger than 0. 1. Okay, we're now going to look at the sine of f double prime. So we're going to look at the sine of the derivative itself. Okay. So look, y'all, I'm going to come back over here. Let me turn this guy on again. Go to my y equals. Let me clear that out. I'm going to have x squared plus x. Okay. Enter that in. Quit. All right. Go to y bars. Let's evaluate this at the first value we said was -2. Okay, so -2, I'm coming up with a positive value. Okay, we're going to do this at -0.5. Coming up with a negative value. And then I'm going to do this again at 1. And coming up again, positive value. Okay. Okay, concavity of f. If the sine of the derivative, y'all, is positive, this is concave up. Okay. If the sine of the second derivative is negative, this is concave down. And if the sine of the second derivative is positive, again, this is concave up. It doesn't look like a very pretty use. Let me fix that. Okay. So now, remember what the intervals I'm looking at, y'all. These are my intervals. From negative infinity to negative 1, from negative 1 to 0, from 0 to infinity. Okay. So now, when I zoom out over here, it says it's concave down over which interval? Between what two numbers? Negative 1 and 0. That's when it's concave down. Okay, it's concave up over which intervals? Yes. Negative infinity to negative 1. When else? 0 and positive infinity. Very good. Guys, again, I really want to emphasize something. Those are my critical values, right? A lot of times, just because the way we draw this thing, we have the -2, the -0.5, the 1, people want to use those numbers as your intervals, but those are just the test values, right? Those are just the test numbers. So the interval is really from negative infinity to negative 1, from negative 1 to 0, from 0 to infinity, right? Those are the intervals that I'm looking at. Does that make sense? Jennifer, am I doing okay? Did I lose you at some point? Okay. Are you okay how we got these signs here? Okay. So if the sign of the second derivative is positive, then the concavity of my function f is going to be concave up. When the derivative is negative, the second derivative is negative, then my graph is going to be concave down. And when my derivative or second derivative is positive, my graph's going to be concave up, right? Yes. Okay. So when is it concave down? When I pick a number between -1 and 0 in that interval. And that's why right here, we said it's concave down over the interval from -1 to 0, because anytime I pick a number between -1 and 0, and look at the number we picked. We picked -0.5, but we really could have picked -0.75, you know what I mean? Because it's just a test number. It just happens to be a number in that interval. So that's why I was really trying to emphasize that those are my intervals, right? So like if it helps, put a big -1 right there, put a 0 right there, whatever it does, right? To let you know that, hey, that's the interval that I'm looking at. These are just my test numbers. You know what I mean? So like instead of 1, we could have picked 100, right? We could have picked any number bigger than 0. We could have picked 100. We could have taken 0.001, and we still would have come up with a positive value. So that's what we're looking at. Yeah, that's why. So yeah, it gets a little confusing because a lot of times we do want to use those numbers. Remember, those are the test numbers. Those are just the numbers in those intervals, right? And we can choose any number we want as long as it happens to fall between -1 and 0, right? So we could have picked -0.75, we could have picked a -0.25, you know what I mean? We could have picked a -0.1, as long as it's between -1 and 0. Yeah. Pi would be a number bigger than 0. You want to plug in pi? Go for it. What are you looking at? You're only looking at the what, though? The sign, right? So what's the actual value? Nobody really cares. We're just looking at the sign. Good question. Okay. So next piece here, y'all, talks about something called the second derivative test. So I know there's the first derivative test, then we do the second derivative for concavity, but there is something called the second derivative test. And it says, suppose that the first derivative at a particular value is 0. What that tells me, y'all, is that's going to be a critical value. Okay, so we're just looking at a particular critical value. If we evaluate the second derivative at that critical value, then the graph of f is going to have a local minimum if the second derivative is positive. If the second derivative of that value is negative, then the f is going to have a local maximum. And if the second derivative at that particular value is 0, then the test is inconclusive. We can't do anything. Let's take a look at what I'm talking about here. Okay, so here's the first example. It says, given the function g of x equals 8x to the third minus 12x squared minus 480x, let's find the first derivative. Okay, that we know how to do. G prime of x, let's see, 24x squared. What comes next? Okay, there we go. Okay, that's the first derivative. That's what we're going to plug in right here, y'all. 24x squared minus 24x minus 480. Okay. What do you mean? Well, there's nothing to simplify at this point, right? Remember, you only simplify if you're solving an equation, right? So right now we're not solving anything yet. But look what it says. Notice that the derivative is equal to 0 when x equals -4. Now, guys, there's a little bit of an assumption going on here. It says, notice that when the derivative is equal to 0, what does that mean that they're doing? That means that they're taking 24x squared minus 24x minus 480, and they're setting that equal to 0, right? If I was going to solve this problem, now, what would be my first step in solving it? What would make this problem easier for me to do? Simplify. Divide everything by what? Let's divide everything by 24. Okay. All the way across. 44. Okay, and then we would end up with an x squared minus an x minus 20 equals 0. Okay, guys, I'm going to ask you for flavors. Remember, x and x. I'm looking for two numbers that multiply to what? -20. Very good. And they have to add up to what number? -1, right? What two numbers do you know multiply to a -20 and add up to a -1? Close. -5 and a 4, right? Because when I add them, either way, I'll multiply by -20, but to add them, these will give me the -1, right? Okay, guys, when we set each part equal to 0, y'all agree we're going to get two numbers, x equals 5 and x equals -4? Okay, I want you to look at this sentence that they wrote right here. Notice, the derivative is equal to 0 when x equals what number? Hey, that's the number. That's one of the numbers we got, right? There happened to be another one, but they're talking, right now they're just discussing that one. Okay, so now it says, we want to know whether there's a local min or a local max. So we're going to use the second derivative test. So now what we want to do, if this is my f prime, or g prime in this case, we want to find g double prime. So we want to take the derivative of the derivative itself. So question, what is the derivative of 24x squared? 48x, okay? And a minus 24, and the 480 part goes away, right? So we just took the derivative of the derivative. Okay, now y'all, what we're going to do, we're going to evaluate that function at -4. So 48 times -4 minus 24. Positive or negative? Positive 168? 48 times what number? Times -4 minus 24, right? -216. There we go. Okay, so -216. All right. Let's see. Based on the sign of this number, does it mean that the graph is going to be concave up at x equals -4 or concave down? Okay, if it's negative, is it concave up or concave down? Concave down, right? So we're going to put concave down. Okay. All right. Now, it says, based on the concavity at x equals -4, does this mean there's a local min or a local max? Okay, take a look, y'all. When we take the derivative, notice the number we came up with. We came up with what kind of number? A negative number, right? If the derivative is negative, then we have a local what? local maximum. So right here, we're going to put maximum. And there we go. Does that make sense? Jennifer, we're doing okay? Just checking the speed. We're good? We're all good here? Everybody got a thumbs up? Awesome. Let's see. I want to just double check with those of you guys who are at home. I know Matias, you're there. Let's see who. Matias, Noel, are we doing okay so far, y'all?
Yes, sir. I'm all good. Thank you.
Oh, hold on. Let me turn up the volume a little bit. I'm sorry. Go ahead.
I'm good.
Okay. Noel, we're doing okay? I'm gonna say
Yes, sir.
All right, just checking with you, Noel. Just want to make sure you're good. Okay, so look, y'all. Same type of problem. Same thing we just did before. Let's go through this problem. This might even be. Oh, we got 2 more. 3 more. 4 more. Oh man, we got more. Okay. I don't know why I thought we were almost done. It's all right. Good, good, yeah. Okay. Yeah, again, y'all, I'm taking the problems directly out of the homework, just trying to give it to you as direct as I can. But let's go through this. We did that one. We should be able to do this one the same way. Okay, let's find our first derivative. Let's do this in pieces. All right, y'all. What's the derivative of 8x to the third? Excellent. The derivative of a minus 12x squared? Negative 24x. And the derivative of a minus 144x is a, there we go. Okay, look what they tell me. Notice g prime of x is equal to 0 when x equals 3. That means g prime of 3 equals 0. Guys, remember what we did a while ago? We took the derivative, we set it equal to 0, we solved it, and that happened to be one of the answers, right? I don't necessarily need to do that because they've already told me that that's one of the answers, okay? So now, look at the second part. The second part says, can we find the second derivative? Yeah, we know how to do that. What's the derivative of 24x squared? 48x minus 24. Okay, we're going to do the same thing here, y'all. We're going to evaluate that derivative at 3. So we're going to take 48 minus 3, or 48 times 3 minus 24. So 120. There you go. Okay, look at the second derivative. If the second derivative was positive, would my graph be concave up or concave down? Concave up, right? If my second derivative is positive, my graph is concave up. If my second derivative is negative, y'all, my graph is concave down. Okay, now, it says based on the concavity at x equals 3, do we have a local min or a local max? So let's come back over here. I'm going to come back to that second derivative test. When we plugged in the derivative at that value, we ended up with a positive number, right? This means positive, this means negative. If it's positive, we have a local what? A local minimum, right? So right here, y'all, we're going to say there is a local minimum. Okay? Okay. So second derivative test, y'all. I'm just going to write this down here just so that we know. When the derivative is positive at that value, we have a minimum. When the second derivative is negative, we have a max. If the second derivative is positive, the graph is concave up. And if the second derivative is negative, the graph is concave down. Okay? So I'm just writing that as a little side note so that I have that as a reference. I don't have to keep scrolling back up and down stuff. Okay? So look what it says. Suppose f is a function. It's given as, and here's my function right here. It says, which of the following is true? We have a relative maximum at x equals 3, a relative minimum at x equals 3, or we don't have a maximum at x equals 3. Okay, so first thing I'm going to do, y'all, again, if I'm sitting where you're sitting, this would be my first step. My first step would say, let me clear this out. Let me enter in the function that I have. So 3x to the fourth minus 16x to the third plus 6x squared plus 72x minus 4. Okay, so there's my function. Let me quit that. All right, let me go to y bars. Let me go to my function. Okay, I want to evaluate this at what value? What's the x value they're giving me? 3. So we're going to plug in this thing at 3. Okay, look at that answer I came up with. 77. Positive or negative? Positive. Okay. If it is positive, this means positive, this means negative. We have a what? Oh yeah, you're right. My bad. Oops. Oops. Yeah, you're right. I got to do the derivative. Sorry about that, guys. We got to start taking some derivatives. I was like, this is too easy. Yeah. Well, I'll put it this way. We'll find out if we'll do our derivative right now, but we know that the value is going to be, when we evaluate it, it would be 77. Whether it's a max or a min, hopefully it's a max. I don't know. We'll see. Okay, so let's see. Let's take the derivative. You're right, guys. I don't know. Brain fart. Okay, let's see. First derivative. What's the derivative of 3x to the fourth? Excellent. Minus, everybody agree, 48x squared plus 12x plus 72. Okay, now let's do double derivative. This is the one that we need, right? Okay, so this here should be 36x squared minus 126 with an x plus 12. Okay, that's the one I got to evaluate, right? Okay. Something I was like, no, that's too easy. Okay, so let's see. 36x squared minus 126 with an x plus 12. Okay, there we go. You're right, 96. Sorry about that. Excuse me. 96. There we go. Okay, let me fix that again. Oops. Y equals, here we go. Delete, put a 9 there. There we go. Okay, so let's quit that. Come back here, y bars. We can evaluate our second function now at 3, right? Okay, at 3. Positive or negative? Positive. Okay, so if the derivative is positive, we have a what? A minimum, right? So we're going to say we have a relative minimum at x equals 3. Excuse me. Guys, there's actually a third case scenario here, is that if the derivative is actually equal to 0, then we say inconclusive, right? What does it tell me? It doesn't tell me anything. Then I would have to go back and use first derivative test and that kind of stuff, right? Yeah. Okay. Let's see. Okay, so here we go. Here's another problem. Take a look at this one. It says, suppose f is a function. So remember, f prime at 7 is equal to 0. Remember what that means. That means that my critical value is when x is equal to 7. So the critical values, y'all, again, just something to think about. The critical values occur when the first derivative is equal to 0. So I know that one of the critical values, or at least the critical value that I know in this case, is at 7. And now what is it telling me? It's telling me that the second derivative of that value is 3. Is that value positive or negative? Positive. So remember what we said. If the second derivative is positive, then we have a what? A minimum, right? So back over here, y'all, we're going to say we have a minimum at x equals 7. No. Probably just the AC. Same thing here. Take a look. Suppose f is a function where the first derivative at 3 is equal to 0. That means my critical value is x is equal to 3. When we evaluate the second derivative at 3, look at the sign of the value we're coming up with. We're coming up with a negative value, right? So look, y'all, I'm just going to scroll one more time. If the second derivative is negative, then we have a what? Then we have a maximum, right? And guys, all I did, I just copied that little piece from right here. Yeah, all I did is just kind of rewriting it so it was a little bit easier for me to do, and so I don't have to keep scrolling back as much. Okay, so we're going to say that this one has a maximum, right, at x equals 3. Alrighty. Okay, so let's try this next one here. And it says, let's find the first derivative of the function. Okay, so let's do it. 12x squared minus 36x minus 120, right? Okay, let's take a look. What's the second derivative now? 24x, good. Minus 36, good thing, y'all. Okay, now we want to evaluate that at negative 2. Okay, so 24 times negative 2 minus 36, that's a negative 48 minus 36, negative 84. Okay, if my second derivative is negative, is it concave up or is it concave down? Down, very good. Okay, if the second derivative is negative, do you remember, do we have a maximum or minimum? Maximum. Are we done now? Parece que sí. There we go. Okay, so guys, let me ask you a question. Does 4.5 make sense? I know it's a little bit of a longer section, just because we had so many problems, but I hope that you realize as we're going through the problems, there was a couple of things we were doing. In the first two problems, though, we find the derivative. We set the derivative equal to 0 to find a critical value. We draw a number line, and we break that number line, for the most part, y'all, into 3 pieces. From negative infinity to the first critical value, between the first critical value and the second one, and then from the second critical value to infinity. Then we pick test numbers, so any number in that first interval, any number in the second, any number in the third. We evaluate the derivative at those test values because we're looking for the sign of f prime. And if the sign of f prime is positive, that means that the function is increasing. If the sign of f prime is negative, the function is decreasing, so on and so forth, and then we can find our maximums and minimums. And guys, again, one thing, I just want to really emphasize this because this helped me so much, like close to like 30 years ago when I had the class, was doing this. Was when I draw like this picture right here, let me just kind of clean this up a little bit. But this helped me like tremendously, like saying, okay, look, the graph goes down, the graph goes up, the graph goes down. And then just doing something like this, like, oh, look, what's happening? Oh, it's doing that. Here's my minimum, here's my maximum, right? Like just drawing that simple thing helped me out so much and understanding, here's my, oops, man, I can't even write today. Here's my min, and there's my max, right? Just doing that helped me out so much, right? So I want you guys to have that same kind of a good experience, and hopefully as you're going through 4.5, this stuff makes sense, okay? So guys, I had made a little calendar. I think I have it at home, but for the most part, from here on out, we're doing like one section a day. I think there's going to be one day where we're going to, 1 week where we're going to do like 3 sections in the week, but for the most part, the pace of our class should be pretty comfortable, okay? And again, that's one thing I really want to emphasize. I want to make the pace comfortable. You know, it's not so much like, I mean, we're going to get through everything, but I would much rather the pace be at a comfortable pace instead of like rushing through it and stuff. Anywho, that is it for us today, guys. Let me go ahead and stop recording.